Thank you. Well, now I'm driving even farther from algebraic statistics. So this is just computing geometry. Since I think I'll change a bit the outline of my presentation, but let's try to make it work. So. Computing the topology of an algebraic curve is an algebraic real plane curve. Is something that has been there for several decades, and well, usually it's just taking the implicit equation, and it's a first step to know the real shape of the curve. I mean, it's interesting to have the important points, which are the singularities of the curve, and knowing something certified instead of just working numerically. But some other times it's the only knowledge we need. Usually, well, my experience with computing the topology of an algebraic plane curve is with sweeping algorithms. There are others, and there are others that work locally and with boxes and so on. But the main idea is that we sweep the plane in the direction of the horizontal axis, and the idea is to find the in the general point of the sweeping, we would find in the vertical line that the points are regular, and the number of branches of the curve is preserved. There are some special lines where some branches even join or disappear or are created. So, for example, here, then there is no micro. So, in this vertical line, in the vertical line of this point, when we sweep from the left to the right, two branches are created in this, let's say, x-extremal point. All right, this leftmost point of this particular neighborhood of the point is two branches are created when we sweep from the left to the right. All right, so this would be the critical points, and the vertical lines where those critical points are would be called the critical lines. All right. So when we found the critical lines, and inside of them the critical points and the non-critical points of those lines, we have to count the number of branches to the left and to the right of this vertical line. All right. Then we find how many branches go to each critical point from each of the sides. All right. And to the other points. Well, for the other points it's easy, because if we have a regular point, just one branch comes from the left, and the other and one branch departs to the right. All right. And when we found this, we just have to join stuff. All right. So essentially, we have the critical, the vertical lines. I forgot to add a thing to this picture, which would be how many branches I have here to the left of the leftmost critical line, and how many branches are in the middle. Maybe I can use the pointer here. So I have one branch to the left of this critical line, and three branches to the right of these critical lines. In this case, I have not, my decision is immediate. I have one regular point in my critical line and one critical point in my critical line. So I know that my regular point needs one branch from the left and one branch from the right. All right, so any other stuff go to the critical point. All right, so when I have when the curve is in the so-called general positions, this means I don't have too many critical points in the same vertical line. This step 4 is automatic. It's automatic. So I don't need to think on geometry to complete that. No need for computations. Everything can be done directly. Fortunately, generally a general change of coordinates allows me to put my curve in general position, and well, this is theoretically not a problem. The general position for me in this case is defined when as the condition of having no real vertical asymptotes, all right, and no real co-vertical points also no real pairs of points in the same pairs of critical points in the same critical line, all right. I mean, it's what allows me to make step 4 automatic. All right. Well, this was said before. Sufficient conditions for the absence of vertical asymptotes is that just the homogeneous component of highest degree of the implicit equation of my polynomial curve is just the it has a non-zero coefficient for the monomial, which is the vertical variable to the highest power. All right. So this is easy to check from the beginning, and you can change coordinates easily. However, the second condition is usually found when we have done all the heavy computation and we end up at a critical line checking that, unfortunately, it has two co-vertical critical points. All right. So in general, this second condition is an unpleasant surprise when you have performed many of the computations you had to do. All right. So now is when I create the mess. So let me motivate why I am trying to avoid this condition of general position. All right. So if we consider two ellipsoids given by two matrices in the three-dimensional space, the behavior of the index function of the pencil generated by such ellipsoids is useful for the determination of the relative positions of those ellipsoids. If one is inside the other, or there is a kind of tangency inside, or there are some part of the ellipsoid inside the other going with a tangency or whatever. And the equation is that determinant, which is a quartic, which is known to have no vertical asymptotes because it's easy to see that the highest that the degree on lambda and both lambda and mu is 4, since the matrices are of size 4, and a priori it can admit co-vertical critical points, and in this case, changing coordinates misses some information that it's interesting for us in order to compute the relative positions of the two ellipsoids. So in some cases, general position is not a luxury we can afford. All right. So now I come back again. So that's a bit about, yeah. So what we want is, let's now consider a curve whose implicit equation is given by a polynomial p. We know that the sufficient condition to avoid vertical asymptotes is that the degree of p is the degree in the variable y of p, and we know that the critical points, the points where branches are collide or are generated, are those points which are solutions of the system of equation given by the polynomial and its derivative, partial derivative with respect to y, well, to the vertical variable. And well, when we saw the referee report for this contribution to this Congress, we found that recently other authors have avoided critical positions for sweeping algorithms successfully. They included some difficult computations because they worked for general cases, but well, what we wanted is not to introduce some techniques to manage a bit more easily than them these coverticalities of critical points in general for low degrees. All right. So well, let's see how we can manage this. So for the first step is to say that for critical points, it's usually possible to find explicit description in the sense of rational functions, or perhaps not rational function, giving us the critical point in the critical line x equal to alpha. If we know that the critical line x equal to alpha, we can find the number beta, which is which completes the critical point with an explicit expression. All right. So in general, when beta is the only point, the only root of its multiplicity of the polynomial of the restricted polynomial to the vertical line, it's easy to compute some greatest common divisors of polynomials and find a rational expression for beta in terms of alpha. All right. Moreover, for conics, cubics, and quartics and quintics, due to the low degree, there are fully characteristic. There are easy expressions which are not always rational. For instance, if we consider a quartic polynomial, we can define the zero subresultant as just the discriminant of this polynomial, so the resultant of the determinant of the Sylvester matrix associated to the polynomial and its derivative. There are some generalizations called subresultants. The first subresultant is the determinant of this, well, that determinant I show here. The second subresultant is this guy here. Well, the first subresultant, the zero subresultant, maybe it was interesting to have it written here, but it's the same, but it's at 0 degree polynomial, or so it's just a number depending on the coefficients. All right. So the point is that generically the first subresultant is a degree 1 polynomial, the second subresultant is a degree 2 polynomial, and when the first subresultant and the resultant, the discriminant, are 0, then the second subresultant is the greatest common divisor of p and p prime. So if this polynomial has two different roots, then it means that my polynomial was this kind of polynomial. All right. So well, finally, we can explicitly with a root find an expression of for my polynomial. So. Sorry for the coordinate I needed. So finally, I'll skip then the ramification points that is already done in this paper. But well, essentially, it takes use that locally we can find. Well, let me check this. Oh, here we have that. Here we can use, when my point is not singular, we can use the implicit function theorem to use the partial derivatives of the polynomial of the implicit equation to use the higher order derivatives criterion in order to see if this is a maximum when considering x as a function of y, or a minimum, and to check if the two branches going to the non-singular critical point come from the right, or from the left, or from the right. All right. So now I delve fastly. The point is that in quartic, when we have low degree, the singular points are easy to treat, because we have explicit expression and we can compute the branches in there. So there is an immediate case that's when we have only as many branches as the regular points. We have nothing to link to any critical points. If we have coverticalities in low degree, we know that these points are of small multiplicity. I mean, if I have two covertical critical points in a quartic, these roots are of degree 2, because I have a quartic polynomial. So if I have 4 branches, each point must receive 2. The main case here to think is what happens when I have just 2 branches. So since I have an explicit expression, I can take the lowest homogeneous component of the polynomial when moved to the origin, and just saying if the branches are real or complex, I know if it should receive branches or not. The point is that I could have this evil case of 2 cusps, and the main way to proceed is just, well, move a bit, not too far from it, and find where is the derivative curve with respect of the arcs of the original curve, depending on how many branches of the blue curve I have above or below the branches of my black curve. I know if the branches go to the upper point or the lower point. And well, the case of quintics is a bit more tricky, but essentially uses the same ideas, so I'll stop here.
Thank you. Are there any questions? Do you have a picture of the quintic?
No, I haven't got a picture of the quintic, sorry. The point is that there is another branch.
Okay.
There are 2 possible cases. In a quintic, there is if you have degree 5 in the vertical variable, then you have a regular point. Or you have either a triple point and a double point. So you know the triple point at least gets one branch, all right? And later you proceed in the same way as in the other case, in the case of quartics, because you have just to remove that branch which goes to this triple point. And in this case, moreover, the explicit expression is rational, because the degrees are different, So just the greatest common divisor of the polynomial and its second derivative is linear in this case. So you can you have one of the both the roots would be rational in terms of the x coordinate. So you can proceed in mostly the same way, but just knowing that there is another branch which would go either to the triple point or to the regular point that you would add to the two double points. But mostly is the same reason.
Okay, thank you.
Thanks.
Any other questions or remarks? Okay, let's thank Jorge again. Thank you very much.